Hi, in this video we look at an example involving the demand function where it is necessary to use implicit differentiation in two different ways and related rates. We look at a problem taken in TAN, applied calculus. The demand function, typically labeled d of x, for a certain brand of compact disc is given by p, which is equal to d of x, and which is equal to minus 0.01x squared minus 0.2x plus 8, where p is the wholesale unit price in dollars and x is the quantity demanded each week measured in units of 1,000. If we graph the unit price p as a function of the demand x, we observe that the graph of the demand function is decreasing. When the demand is non-existent, the unit price is of $8 per unit and no one wants to buy. The maximum number of discs that can be sold is 20,000, but in that case, they would have to be given away for free. Therefore, if we want to maximize the revenues, we should probably sell at a price that's somewhere between $8 and $0. The first question that we need to answer is the following. If the unit price is decreasing at a rate of 30 cents per week, at what rate is the demand changing when the demand is of 8,000 compact discs? When the demand is of 8,000, x equals 8, and the fact that we are given a rate in dollars per week tells us that this rate is a derivative of the unit price with respect to time, measured in weeks. Therefore, we know that dp dt is negative since p is decreasing. And on the graph, it is clear that a decrease in the unit price will lead to an increase in the demand, x. Therefore, dx dt, the rate at which demand is changing per week, will be some positive number. Let's remember to verify this at the end of our computation. Since the unit price is decreasing at a rate of 30 cents per week, then dp dt is minus 0.3. To find how dp dt relates to dx dt, we need to differentiate the demand equation implicitly. We take derivatives with respect to t on both sides. There's nothing to do on the left-hand side, but on the right-hand side we differentiate each term in the sum, giving a special care to the first two terms by noticing that x and x squared are functions of time, since the demand x varies over time. What is important to notice here is that we're not differentiating with respect to x, so the derivative of x squared is not just 2x anymore, and the derivative of x with respect to time is precisely our unknown in this problem. It is the rate at which the demand varies per week. Right now we do not know it, and it is certainly not equal to 1. Only the derivative of x with respect to x would be 1, but the derivative of x with respect to t is unknown right now. The derivative of x squared with respect to t is obtained by applying the chain rule. Differentiating x squared with respect to x would give 2x, but by the chain rule, differentiating x squared with respect to t gives 2x times dx dt. Finally, notice that the last term is a constant and its derivative is 0. We therefore obtain an equation relating dp dt to dx dt, and that is why we call these types of problems related rates. Factoring dx dt on the right-hand side gives us that dp dt is equal to minus 0.02x minus 0.2, all of that times dx dt. We see that if we know the rate of change of either p or x, we know the other rate of change, and that is why they are related. In our problem, we want to know the rate when the demand is of 8,000 compact discs. When that happens, x equals 8. P is the demand function evaluated at 8, so we obtain its value by replacing 8 in the demand function, given as part of the problem initially. That gives us $5.76 per unit. And finally, dp dt was computed earlier on and is minus 0.3. We can just replace all these values in the equation. Just note that we didn't actually need the value of the unit price, but we may have in another type of problem. And we solve for dx dt, and we get that dx dt is 0.83 repeated 1,000 units per week, or 833 units per week. Remember that we were expecting a positive rate of change of the demand, so this answer at least verifies this. So in a week from now, we could expect that the demand would be of 8,000 plus 833 units per week. To summarize our findings, when the demand is of 8,000 compact discs and price is decreasing at a rate of 30 cents per week, then demand is increasing at a rate of 833 compact discs per week. There are two more questions to answer. First, compute the elasticity of demand when the demand is of 8,000 compact discs. Second, based on the elasticity, decide whether we should sell more or less compact discs in order to increase the revenues. Recall that the elasticity of demand, we need to express the demand x as a function of the unit price p. If we call the demand function d of x, then p is equal to d of x. And when we express the demand x as a function of p, we typically write x equals f of p. Elasticity of demand is defined as E of p is equal to minus f prime of p times p divided by f of p. F prime of p is the derivative of the demand with respect to the unit price p, and that is just the same as dx dp. Notice the difference here compared to the first part of the problem. We had before to compute dx dt, how the price varies in time, but here it is dx dp. That is how demand varies with respect to the unit price. It's not the same kind of derivative, but we face the same kind of problem when we want to compute what it is, since we cannot solve easily the demand equation for x. We use implicit differentiation again. Now this time, we take derivatives on both sides with respect to p, not t. The steps are similar though, and the only real difference is that on the left-hand side, dp dt is just 1. And solving for dx dp and replacing x by 8 gives a value of minus 2.78 repeated. The negative sign makes sense here, since the demand is usually a decreasing function of the unit price. So when the unit price increases, the demand typically decreases, and that is confirmed by the negative value of the derivative. Therefore, E of p is minus dx dp. That's, remember, the same as f prime of p times p over x. And here we're dividing by x, since f of p is precisely the demand x. When x is 8, dx dp is minus 2.78, and we only need the value of p to compute the elasticity. But we had done this in the previous problem by replacing x by 8 in the demand function, giving us a unit price of $5.76. If we replace these values in the formula for elasticity of demand, we get a value of 2. The interpretation here is that when the demand is of 8,000 compact discs, the unit price is $5.76, and if the unit price increases by 1%, the demand decreases by 2%. Since the demand decreases relatively more than the relative increase in unit price, the demand is elastic, and increasing the unit price will decrease the revenues. This also means that to increase the revenues, we have to decrease the unit price, and therefore increase the demand. The optimal demand should be higher than 8,000. It's possible to show by maximizing R of x, which is x times p, and which is x times the demand function, minus 0.01 x squared, minus 0.2x plus 8, and we can do that by setting the derivative of r to 0, that the revenues are maximized when 10,972 compact discs are being sold. As expected, this value is indeed larger than 8,000. Thanks for watching.